Okay, welcome back everybody. We're going to be looking at the third and final part of 1.1 number systems following the new computer science IGCSE syllabus. In this we're going to be looking at how to add two positive 8-bit numbers. We're going to be looking at overflow and how this is caused when we do add two positive 8-bit binary numbers. We're going to be looking at logical shifts on positive binary numbers and how we can multiply binary numbers and divide binary numbers using this method. We're then going to finish off with something called two's complement notation, and this is new to the new syllabus, but this allows us to represent both positive and negative binary numbers. Once we've done that, we should be moving on, sticking with the data representation, but we'll be moving on to text, sound, and images. Okay, so adding binary numbers together. Well, in the normal system, in a denary system, we'd be looking at the units column first of all, and if we have 1 plus 2, obviously that equals 3. It's only when we carry over and we maybe add 9 plus 4 and we get 4 lots of units and 1 lot of 10 that we can sort of draw on that and see similarities in the denary system. So there are some rules, and here we go. We've got 4 rules. If we have 0 plus 0, obviously that's going to be a 0. It's the same in any number system. 1 plus 0, of course, is still 1. But when we get to the next 2, 1 plus 1 would equal 2, which in binary would be 1 lot of 2 and no lots of 1s. And then if we have 1 plus 1 plus 1, obviously this is 3, but 3 is represented as 1 lot of 2 and 1 lot of 1. So if we follow this method, we can look at this sum which we've got here, this 8 bits from 2 registers. Register 1, and I've put register 2 underneath it as a simple sort of addition sum. We can go step by step through this together. So we have 1 plus 0 obviously equals 1. Now we get to the third rule. 1 plus 1 is 2, but that would be no units, no 1s. So we carry over the 2. So 1 plus 1 again. We're going to do the same thing. 0, carry the 1. Here we've only got 1, so we pop that into the answer. 1 plus 1 again. 0, carry the 1. 1 plus 1 again, 0, carry the 1, and now we've got the final rule. 1 plus 1 plus 1 obviously equals 3, so that's 1 lot of 1 and 1 lot of 2 that we carry over, and we can put this into the final column to get the answer 1 1 0 0 1 0 0 1. Hopefully, looking at that, you can remember how you might change this first of all into a denary number, how we could convert that. And also, if we were to divide it in half and split it into 2 nibbles, how we might change this into an hexadecimal. Now, if we were to change the first number, the first digit in that first byte of information and change it to a 1, obviously when we add all these numbers together again, we'd end up with something with a 9th bit, something that's called an overflow. This obviously would lead to errors in the sense that we can't have 9 digits, 9 numbers represented in an 8-bit number system. So we'd end up with problems there, and the system might crash, or it might ignore that extra digit, so you wouldn't get the correct answer. We then move on. So logical binary shifts 1.1.5. Okay, we're going to use this technique to shift numbers left and right, backwards and forwards in a register. Obviously, with binary numbers, things need to be added together, taken away, removed. But in this case, we're going to be multiplying or dividing bytes, in this case, of information. So, if we were to shift the numbers in this system, or shift these 1s and 0s across to the left, we would be multiplying. And you'll see that in a moment. And if we shift them to the right, going down the register, so to speak, then we will be dividing by 2. Well, what does that mean? We have an 8-bit register here below, and it contains the denary number 21. You can see that it's one lot of 16, one lot of 4, and one lot of 1 added together, obviously 21. Now, if we shift these digits to the left, if we move them one space, okay, we're going to get one lot of 32, one lot of 8, and one lot of 2. Now that's obviously 42, which would be twice the value of 21. So 21 times 2 equals 42. When we're shifting, we've got spaces, we automatically put in a 0 into the end column. Now some of you might see this and think, this could cause problems, and it does cause problems. So as a bit shift, an empty position is replaced with a 0. And obviously there are limits in an 8-bit number system as to how many zeros you can put in before it completely zeroes out. So for example, if I was to take this number here, one lot of 64, one lot of 32, and one lot of 16, and I was to move this 5 places to the left, then we would end up with a register full of zeros. Okay, but we've multiplied this number, and obviously when we multiply this number, the equivalent of denary value 112 or 112, when we times it by 2 and 2 and 2 and 2 and 2 again, we're not going to get purely zeros. Okay, so here's some more examples. What we're going to do first of all, write 24 into the 8-bit register. Well, that's obviously one lot of 16 and one lot of 8. Okay, so that's straightforward. We know that. Now we're going to do a logical shift, going 3 places to the left. So we're going up the register. So shifting them 1, 2, 3. As you can see there, it's times 2, times 2, times 2, which would equal 192. So we've times it to 24 times 2 to the 3, which represents the 3 shifts. Okay, 192. Now if we go back to the existing result, the existing register, which was 24, and we go 2 places to the right, you can see there we've gone 1, 2. We're basically dividing. So 24 divided by 2 to the 2 shifts would equal 6. Basically 24 divided by 2 is 12, and divided by 2 again would be 6. Okay, so that's how we multiply and divide using logical binary shifts. Okay, and for the final bit, we're going to be looking at 2's complement on binary numbers, how to represent negative integers when we're using 2's complement. So in this section again, like the others, we're going to assume that 8-bit registers are being used in terms of the questions. The only major difference that we're going to use in terms of these registers is we're going to change the heading of one of the numbers, that being minus 1 to 8. 1 to 8 becomes minus 1 to 8. Of course, that means that we no longer have 255 different character representations, different sequences of 1s and 0s. Because we've got the minus 1 to 8, this refers to everything which has a 1 under minus 1 to 8 is a negative number. Everything with a 0 under the minus 1 to 8 is a positive number. So we basically split 255 into 2 halves. The positives being 0 up to 127, and the negatives being minus 128 all the way up to minus 1. And here we can see that minus 128 would be one lot of minus 128 and nothing in the other columns, whereas plus 127, the sort of biggest positive number we can have, would be no lots of 128 and all the rest of the columns being filled in with 1s. It is important to realise when applying 2's complement to a binary number that the leftmost bit always determines the sign of the binary number. As I've just said, a 1 value in the leftmost bit indicates a negative number, and a 0 value in the leftmost bit indicates a positive number. I can't emphasize this enough. I'm going to try and show you a number here, a representation of 51. And of course, if we look at this, you look and see, okay, we've got one lot of 32, one lot of 16, a 2 and a 1. It is exactly the same as how you would normally do it. There are no negative 128s, there are no positive 128s, in the same way there's no 64s. It is exactly the same. So if we want to represent the number minus 49, we're going to put a 1 under the minus 128. This shows that it's a minus number, and we're going to start with that number, minus 128. We're then going to add to it positive 64. Positive 64 plus minus 128 would give us minus 64. If we then add positive 8 to minus 64, we would get minus 56. Add positive 4, we would get minus 52. Add positive 2, we'd get minus 50. And finally add positive 1, and we would get minus 49. And this is how we represent the minus numbers. We're adding the positive numbers, the ones in green as you can see here, to the minus 128. But that's it. That's how you would do the 2's complement representation of negative numbers. So have a practice, good luck with that, and remember, if there's a 1 there, it's a minus number, and if there's a 0, it is a positive number. But the question will always say this is a representation of a 2's complement binary number. That's it for now. Thank you very much indeed. That, as I said at the beginning, is the end of this little bit 1.1. So thank you very much for watching. Next time, the next video will be 1.2 text, sound and images. If you haven't already, please subscribe. I will be doing these as quickly as possible. I'm trying for 1 video a week, but bear with me. So thank you very much indeed, and I will see you next time. Bye for now.